Hello everyone, welcome to the first lecture in this course on microsensors and nanosensors. So this is the course overview. As I have mentioned in the introduction video also that in first week we are going to discuss the basics of sensors. First we will talk about definition of sensors and then we will see classification of sensors. These classifications are based on different requirements, like if the sensor is if it can convert directly some value to some electrical signal, some non-electrical value to electrical signal, I can call it direct sensor. Or it is a complex sensor, it can't convert some part to some desired part to electrical part. Okay, it can be active or passive depending on how it is utilizing energy, and there can be some other classifications also. It can also be classified based on what it is measuring. It is measuring some physical quantity, I can call it a physical sensor. If it is measuring some chemical component, say for example some gas, some ion or something else, this can be classified under chemical sensor. And if I am using it to measure some biomolecules, I will call it biosensors. So there can be different classification. So in the first week we will get acquainted with this word sensor and its classification. Okay, we'll also learn a little bit on fabrication, that how these sensors are fabricated. Okay, so conventional and non-conventional fabrication techniques, both we will see. Okay, this will include fabrication of the sensors on hard substrate as well as on flexible substrate like PET, even cloth, and say on some stretchable material. Okay, so nowadays you might have seen that people are putting patch of sensors on body. Okay, these patches are nothing but flexible substrate. Okay, in electronics we call it flexible substrates. This can be usually made up of PDMS. So we'll be discussing a little bit on fabrication of both conventional and non-conventional sensors. All right. In the second week, as I have mentioned that we'll be discussing different characteristic of sensors. This characteristic can be of various types. It can be reproducibility of a sensor, repeatability of a sensor, hysteresis error of the sensor, full scale output with full scale input, which is known as span, dynamic range of the instrument, okay, of the sensor, and various other points are there. Okay, so we will be discussing those characteristics of sensors in detail. Okay, so by the end of week 2 you will be acquainted with all these characteristics. So if you are planning to buy one sensor for you, okay, you will be able to assess the sensors that are available in the market on certain parameters. So these parameters are nothing but characteristic of these sensors. So that we are going to discuss in second week. Okay, in the third week we are going to discuss different principle of sensing. This principle are resistive, capacitive, some magnetic, okay, piezoresistive, piezoelectric, all optical, all this kind of principle of sensing we are going to discuss in third week. Okay, and in the fourth week we will be discussing on interface circuit. It can be excitation circuit for the in-house developed sensor, or it can also be amplifiers that can amplify small amount of signals that are usually generated by microsensors and nanosensors. Okay, so those things we are going to cover in week 4. Okay, in week 5 we will be discussing some humidity sensor. This humidity sensor can be based on any of the principle that I have just mentioned for week 3. It can be resistive, can be capacitive, okay, it can be based on some other principle also. Okay, by the way, 75% humidity sensors are capacitive in nature, so we'll be focusing this section on capacitive sensor. However, the chemical sensor will cover the gas sensing part mostly, So these sensors, we will be focusing on 2-terminal and 3-terminal devices. Maybe it's chemi-resistive and chem-FETs kind of devices we are going to discuss in week 5. In the subsequent week, we will be discussing temperature sensor. This temperature sensor can be based on simple thermistor, thermocouples, thermopile, RTDs, and semiconductor temperature sensor, particularly based on p-n junction. Okay. In the 7th week, we will be discussing force sensor. Force sensor are nowadays very crucial, particularly to measure micronewton forces. But before we actually discuss the micro force sensor, we'll try to understand the conventional force sensor based on strain gauge. Okay. So once we understand the strain gauge based force sensor, we will be ready to understand the current micro and nano force sensor based on various transduction techniques, be it capacitive, piezoresistive, piezoelectric, and etc. Okay. Week 8 will be devoted to tactile and pressure sensor. Tactile sensors, in tactile sensor we'll see different type of tactile sensors. Okay. And in pressure sensor we'll see some of the real examples. Okay. So in the 9th week we will be discussing occupancy and motion sensor. This occupancy sensor we will be again recalling in week 11. Okay. These sensors will be based on ultrasonic principles, microwaves, triboelectric motion sensors. Once we will understand all these things, we'll also discuss some mid and far IR based motion sensors. Okay, because they are the future. Okay, all these IR sensors are getting lot of attention in particularly for defense application and all. So we will be covering that in detail. Okay. In week 10, we will be talking about displacement sensors and accelerometers. Okay. Accelerometers behave little different than other sensors, and therefore the definition of their characteristic has little tweak. So I will be defining those characteristic in context of accelerometer so that there is no confusion. Okay. And once we finish this 10 lectures, in week 11 and week 12, we'll see some practical examples. These practical examples will be from 2 sectors. One is from smart building monitoring and second is for healthcare. In the smart building section, will be as I have mentioned, that we'll be discussing on occupancy sensor and little bit on smoke sensor also, because nowadays all these buildings you have seen are equipped with the fire alarms and other things. Okay, it can be in your, you might have seen that in your institute as well as even at your home. Okay, so these smoke sensors has become integral part of our life. Okay, so this practical example we will see in week 11. In week 12, we will be discussing glucometers, particularly based on electrochemical method. We will also see MRI and ECG tools so that this healthcare section is complete. Okay, so this is course overview for this microsensors and nanosensors course. Now let us start this course with defining sensor. Okay. So if I have to define a sensor, sometime it can be very broad. Okay. So if I have to define it, mostly it is defined as a device that receives and responds to a signal or stimulus. Okay. So the definition can be as simple as this. However, if you see, this definition is very broad. Okay. A device that receives and responds to a signal. Okay. So in that sense, if you see, our skin is also a sensor, because it has a sensory receptor and a sensor and a brain. So if someone pinches us, okay, we can immediately, our brain immediately process the information that somebody has pinched you. Okay. So however, for our application, we are not calling it a sensor. Okay. So for us, this definition is pretty broad. Okay. So we have to narrow it down. Okay, we can narrow it down based on various things. Okay, however, before we narrow it down, let's understand the meaning of this word stimulus, okay, or measurand. This stimulus is very crucial because our sensor, I mean, how we are making this sensor, what is the fabrication steps, what is the principle behind this sensor, all these things will depend on what stimulus you are using. Okay, so the stimulus is the, which is a quantity, property or condition is received and converted into electrical signal. So this condition can be anything. It can be humidity in your room, it can be motion of your car, it can be a wind speed that aeroplane is measuring. So stimulus can be anything that is being measured. Okay, some text uses a different term, measurand, which has the same meaning, however with the stress on the quantitative characteristic of sensing. Okay, in this course, since we will also discuss some qualitative sensors, so we will be using mostly the word stimulus. Okay, as I have mentioned that this stimulus can be change in ambient. This ambient can be change in temperature, humidity, pressure around you. Okay, the stimulus can be humidity, it can be light, sound, or other factors that is changing around us. Okay, based on what stimulus you are using, you have a number of sensor. Okay, as I have mentioned that for measuring temperature, you have number of sensors available, RTD, thermistors, and all. Humidity, we have capacitive, resistive, those kind of devices. Similarly, you have fire alarm, accelerometers, chemical sensor to monitor gas, and etc. Okay, so if I have to define a sensor, I can say that a sensor is a device, a system where you have some input physical property in the form of stimulus, and it converts something, it convert that input stimuli to readable output format. Mostly this readable output format for our course will be electrical in nature. Okay, so this electrical signal has to be also compatible with the next stage. So next stage in our sensor system is a readout circuit or interface circuit. All right, so the output of the sensor has to be compatible with the next stage, which is the interface circuit. Okay, so in brief, I can call a sensor as one kind of translator. So this translator translate non-electrical value to some electrical value. Okay, here the word electrical refers to a signal that can be channeled, amplified, and modified by the electronic devices. Okay, say consider a capacitive sensor. Okay, consider a capacitive sensor. As you know that I can the capacitor is defined as for a parallel plate as epsilon A by D. All right, by some mean, say this is a parallel plate capacitor. Okay, this is a parallel plate capacitor, and you have some dielectric material over here. Okay, say this end of the capacitor plate is hinged to some wall. All right, this portion is hinged to some wall, and by some mean this plate is taken towards this side. Okay, because of this the D value is changing. Okay, this D value is changing, and because of this D value the capacitance value is changing. Okay, now if you see, this motion is a non-electrical value. Okay, this motion is a non-electrical value. This motion is getting converted into change in capacitance, and this reflects as change in voltage at the output. Okay, now the change in voltage can be calculated. If the change in voltage is very less, you can have different amplification section after this sensor. Okay, so that's why I mentioned that sensor is one kind of translator. Okay, in sensor you always deal with energy transfer from the object of measurement to the sensor. Okay, it can be vice versa also. It can be the energy transfer can also be from sensor to object. Okay, or there can be no transfer. We'll see that. Okay, sensing is a specialized form of information transfer, and every transfer of information necessitates the transmission of energy. Sensor output signal may be in the form of voltage, current, or charge. Any other form will be converted to these forms. Okay, so in the interface circuit we'll see that how we can develop interface circuits that if the value is not in this particular form, it can be brought back to this particular form. Okay, so in a sensor, transmission of energy can be in different ways. It can have a positive sign, it can have a negative sign, and it can have a zero sign. Say for example, I have a sensor, okay, here, and I have a object over here. Okay, this sensor is trying to find this object's position. Okay, this sensor is trying to find this object's position, and this object is moving in some trajectory. Okay, this trajectory. All right. Okay, based on its movement, okay, the information that it is exchanging with the object will keep on changing. Okay, so for some section it can be so it can have a movement like this also. Okay, or at some angle also. Okay, all right. So for some position, this value say if this sensor is sensing the temperature of this object. Okay, the sensor is trying to detect this this object by measuring the heat exchange with the sensor. Okay, at certain positions of this sensor, this value can be positive. For certain position, it can be negative. For certain position, the heat exchange can be zero also. Okay, one of the such example is a thermopile infrared radiation sensor. If you don't know about thermopile sensor, don't worry much. Thermopile is nothing but a series connection of thermocouple. Okay, we'll discuss thermopile when we will discuss the temperature sensor in week 6 in our microsensors and nanosensors course. But for the time being, you understand that thermopile infrared radiation sensor is a sensor which can measure the temperature of something. Okay, so this is a typical thermopile IR sensor. Okay, you know that infrared radiation carry heat. Okay, so it's basically a heat sensor. Okay, we'll see in detail in week 6, but I'm taking this example to understand this information or transmission of energy from sensor to object. Okay, so consider the example of thermopile infrared radiation sensor. This sensor will produce a positive voltage when the object is warmer than the sensor. Okay, this will produce a positive voltage when the object is warmer than the sensor. Means the infrared flux is flowing from the object towards the sensor. Okay, now consider the other case. Okay, when object is cooler than the sensor, what will happen? When the object is cooler than the sensor, the voltage will be negative because infrared flux flows from the sensor to the object. Alright, so you have seen two different information with two different voltage. When you have positive voltage, you have understood that infrared flux is flowing to the sensor, means your object is warmer than the sensor. Okay, so you wanted to know that if object is cooler or warmer than the sensor, it's clear to you that your voltage is positive means your object is warmer than the sensor. When the voltage is negative means your object is at lower temperature than the sensor. However, there can be a case when the flux exchange between object and the thermopile IR sensor is 0. Okay, when there is no information exchange between them, I mean, it doesn't mean that there is no information exchange between them. It means that the object and the sensor are at the same temperature. So that is why in the previous slide I have mentioned 3 different cases: positive sign, negative sign and 0 sign. Positive sign for thermopile IR sensor that we have just seen means the object is warmer than the sensor. Negative sign means object is cooler than the sensor, and 0 sign means both are at the same temperature. Okay, this is very important to understand. Okay, once I understand that a sensor is a converter from one form of energy to electrical, okay, I am ready to differentiate between a sensor and a transducer, because sometime there it can be very confusing. Okay, because there are various courses also on sensors and transducers, sensors and actuators. Okay, so differentiating between these terms are very crucial. So we will discuss in very brief that what is the difference between a sensor and a transducer, what is the difference between a sensor, transducer and actuator. Okay, once it is clear to us, then we will move towards classification. Okay, basically both sensor and transducer are energy converters. Okay, sensor converts any type of energy to electrical signal. Please remember that sensor converts any type of energy into electrical signal. Not to mention that this electrical signal should be compatible with the next stage. I am not using that word now because I assume that you are now acquainted with these terms. Okay, so sensor converts any type of energy into electrical signal, whereas a transducer converts energy from one type into another. Okay, this type can be anything. It can be, say, from mechanical energy to heat energy, or heat energy to mechanical energy. Okay, it can be, say, chemical energy to mechanical energy. Okay, can be of various type of conversion, but not conversion from non-electrical to electrical. Okay, I hope that difference between a sensor and a transducer is clear. One example of a transducer is a loudspeaker. Okay, we all know that how a loudspeaker work. Okay, it converts electrical energy to sound energy, right? These transducers or loudspeakers are also known as electroacoustic transducers. Okay, when you pass this electrical current through a coil of wire placed in the magnetic field, coil exerts force and causes vibration, which creates sound waves. Okay, that is how a loudspeaker work in nutshell. Okay, so basically what you are doing is you are converting electrical energy to sound energy. Okay, so means you are converting some form of energy to another form of energy. If it is not electrical, means I am considering a generic statement that some form of energy to another form of energy. Okay, so this is an example of a transducer. Fine. Then there is one more term known as actuator. Okay, actuator is actually a type of transducer. Okay, but it is just opposite to sensor. Okay, when I say opposite to a sensor, means it usually converts electrical signal to non-electrical signal. All right, so it converts electrical signal to a non-electrical signal. Now you just see loudspeaker, you have provided some electrical current which has converted to vibration and then to sound wave. Okay. Similarly here, electrical motor. Okay, this is a perfect example of actuator where you have some movable part also, so which converts electrical energy to mechanical rotation. Okay, so you have provided some electrical energy to some potential to say a motor, okay, and it is converted into rotation. Fine. So this is an example of a actuator. So I hope that the difference between a sensor, transducer and actuator is clear to you. Okay. There are other examples also to understand this. Okay. Say consider this pneumatic actuator. This is a perfect example of actuator, which is these pneumatic actuators are enabled by electrical signal. Okay. So you provide electrical signal and the piston move back and forth in the chamber. Okay. So this is again another example of a actuator. Okay. So if I have to summarize, I can say that any useful energy is converted to another form of energy. The device is a transducer. A sensor converts any useful energy to electrical energy, while an actuator converts electrical energy to another form of energy. Okay. Now, once these definitions are clear to me, okay, I will move ahead towards classification of the sensor. Okay. This classification that we are seeing right now is based on three things: based on transduction function, based on energy, and based on selected reference. Okay. Based on transduction principle, I can have transduction function, I can have a direct sensor and a complex sensor. Okay. Based on the energy used by this sensor, I can have a active sensor and a passive sensor. And based on the selected reference, usually I have a absolute and a relative sensor. We'll see them one by one. Okay. Let us first understand the difference between a direct sensor and a complex sensor. See the figure at the screen. Okay. You have a signal S1. Okay. Some user has to convert this signal S1 to S4. Okay. There is no sensor available, okay, which can convert this sensor signal S1 to S4. Okay. Therefore, what he has done is he has used a transducer 1 and transducer 2. Okay. In fact, signal S1, conversion of signal S1 to S3 is also not possible. Alright. Therefore, he has to use two different transducers, transducer 1 and transducer 2. By using transducer 1, he has first converted signal S1 to S2. Okay. Now, S2 is compatible with the input of transducer 2. Alright. So now, he has given this signal S2 to transducer 2. Please note that S1, S2, S3 doesn't have to be electrical in nature, okay, because you are dealing with transducers right now. Okay. So S1 has been converted to S2 and S2 is now getting converted to S3. Okay. Now there is a sensor available which can convert this non-electrical value S3 to a signal S4. S4 is essentially a electrical signal. Okay. So I am calling this sensor a direct sensor. Okay, which is converting non-electrical S3 to electrical signal S4. Okay. However, the complete system, this direct sensor plus this transducer 1 plus this transducer 2, it makes one sensor, and that is a complex sensor. Okay. So a sensor may consist of several transducers and a direct sensor. Direct sensor converts the received signal to electrical input. Just now we have seen that. Transducers can be part of a complex sensor. So you have just seen that transducer 1, transducer 2 and a direct sensor makes a complex sensor. I hope it is clear. To define, a direct sensor converts a stimulus into an electrical signal or modifies an electrical signal by using an appropriate physical effect. Whereas a complex sensor needs one or more additional transducer before a direct sensor can be employed to generate an electrical output. Okay. So this is how it is defined, and this is how you have to understand these sensors. Okay. In this course, we will be discussing mostly direct sensors. However, we will also discuss several complex sensors. Okay. Example of this complex sensor can be a chemical sensor. Okay. You can understand this chemical sensor as a device which produces electrical signal in response to a chemical reagent. Okay. Say consider dissolved oxygen sensor. Okay. So we know that dissolved oxygen is responsible for aquatic life. Okay. So if you want to measure the dissolved oxygen, you have to do electrolysis of oxygen. Okay. So first what you are doing is in these chemical sensors, what you are doing is you are converting this chemical reaction to heat, and then what you are doing is you are converting this heat energy to electrical energy. So it has essentially two parts. One part which convert the energy developed in a chemical reaction to heat, which is basically a transducer, because you are converting non-electrical value to another non-electrical value. Okay. And then you have another sensor which is a direct sensor basically, so which can convert this heat generated in this chemical reaction to a electrical value. Okay. So you can understand this chemical sensor as a series of transducer and a direct sensor. I hope this example is clear to you, and direct sensor and a complex sensor definitions are clear. Okay. Another way to classify these sensors is based on the excitation energy provided to these sensors. Okay. Based on that, you can have active sensor and a passive sensor. An active sensor need external power. Okay. It need some excitation signal for its basic operation. Okay. Excitation signal is modified by sensor's parameter to produce output signal. This modulation carries information of the measured value. Okay. As you have just seen that excitation signal is modified by sensor's parameter to produce output signal, these sensors are also known as parametric sensors. Okay. And one good example of this active sensor is a thermistor. Okay. Which is a temperature resistive sensor that we are going to discuss in week 6. Okay. Then with active sensor you have a passive sensor also, which doesn't need any additional energy source. Okay. It can directly produce electrical signal in response to external stimuli. Okay. Here the input energy is directly converted to output signal. Okay. Most of the passive sensors are direct sensors. Okay. Like a photodiode and a piezoelectric device. Okay. I hope that the difference between active sensor and passive sensors is clear to you. There is another way to classify these sensors based on reference. Okay. They are absolute sensor and a relative sensor. Okay. An absolute sensor detects a stimulus in reference to an absolute physical scale. Okay. It is independent of the measurement condition. One example is again a thermistor. So its electrical resistance directly relates to the absolute temperature scale. Okay. Then a relative sensor is measures stimulus relative to the surrounding ambient. Okay, and one example of relative sensor is a thermocouple. Okay, thermocouple produces an electric voltage which is a function of temperature gradient across its wire. Okay, therefore a thermocouple output signal cannot be related to any particular temperature without referencing to a known baseline. Okay, so baseline is very crucial for the relative sensors. Okay, most of the optical sensors that we are going to discuss in this course will be a relative sensor. Okay, consider one example of, say, NDIR sensor, non-dispersive infrared sensor. Okay, NDIR sensors are nothing but they are based on infrared. Okay, say consider a NDIR gas sensor. Let me take a pen. Consider a NDIR sensor. So I have a cell in which I have some gas molecule. Okay, I have a infrared source. Okay, I have two infrared detectors over here. Okay, two infrared detectors over here. One is to detect reference and another is for detection of active signal. Okay, now say a signal S1 is detected at reference at the reference infrared detector. Okay, and a signal S2 is generated at the second infrared detector. Okay, I can compare this S2 with S1. If I compare them, I may know that there has been some absorption by this gas molecule or not. If there is no gas here, absolutely, okay, S1 will be equal to S2. Okay, if this cell has some gas molecule and it absorbs an infrared, okay, S2 will have different signature than S1. All right, therefore reference for this optical sensors are very crucial. Okay, and they fall under a category of a relative sensor. Okay, another example of the absolute and relative sensor is a pressure sensor. Okay, an absolute pressure sensor produces signal in reference to vacuum. Okay, where an absolute zero on a pressure scale. Okay, while a relative pressure sensor produces signal with reference to selected baseline. This baseline can be chosen by you. Okay, this is of course not zero pressure. For example, it can be a atmospheric pressure. Okay, so with this I hope that the definition of relative sensor and absolute sensor is clear to you. Okay, thank you. We will meet in the next lecture. Thank you.